introduce this new center, CNRS Center, who is funding in large part this meeting. And so Amanda Smith, who is here, is also a representative of the center. What is exactly your title? Your project manager, right? So she's the boss, and I'm a member of the scientific committee. So it's, as I say, it has just been created recently. It's a center without wall, and it's an interdisciplinary center, so AI for science and science for AI, so it's like going both ways. So this workshop is a perfect representation of what we want to do with this center. And this workshop is the first one that is funded by the center. So we are really like the first to experience the new activity of the center. So if you want to know more, you can go to this address. Maybe the simpler is to type ASSAI Center on Google, and you'll find the web page, the CNRS web page with all the details and more information than what I would tell you today. I'm sorry. Other direction. Oops. So actually, it's a long reflection. More than 2 or 3 years ago, people at CNRS started to think about what they can do to promote AI in science activities. So there was a working group created at CNRS. And really the goal is to try to encourage interaction between all the disciplines supported by CNRS, which is basically all basic science in France and abroad, and to try to promote new type of collaboration across the discipline. So this, once again, this workshop is a very good illustration of researchers from a broad origin that discuss together. And basically the goal is both to advance basic science, so deep question in each field, but also to try to tackle some strategic question, general question in AI, such as introducing more expert knowledge, having robust model, explainability, ethics, and frugality. So of course, not everything is represented at once in one workshop, but we try to promote workshop which also take a step back and try to study also general questions. Also one goal, so it's not starting yet, but in the long run is to also promote activities across countries to establish some kind of networks between centers. So there's already a discussion with Canada, but of course there would be more discussion. It's just started. This is really the first month where the center is started. So and we are trying you also to give us like some insight and ideas. So if you have some center in your country and you look for some similar center in France, I think ASSAI is truly the first one with such a broad scope. So feel free to discuss with us, with Amanda, with me. You can just drop me an email and I will put you in contact with the board of ASSAI. So just a few boring words about the organization. So one key aspect is that we have a very strong international board that will give us ideas, give us feedback. It will not be an operational board, but it will basically discuss maybe twice a year about strategic question and what type of activity we should promote, or if there are things we should correct to tell us what we should do. And really there is at least one representation for each big area of CNRS. So if you don't know, CNRS is organized in several institutes, and there is one representative for each institute. Also, of course, we have also an executive committee. So the project manager is Amanda Smith, who is here, and there is one director, who currently is Jalal Fadili, who is in charge of course, supervising everything. And I'm one of the members of the steering committees. And once again, it's the same idea. You have members from all scientific institute of CNRS. So I'm representative of mathematics, but there is one in biology, physics, etc. And to conclude, just a few words about the activities we're promoting. The big aspect, I mean, most of the money will go for organization of trimesters. So this is the first trimester that we found. There would be one trimester on causality in next years. And we are currently discussing with organizers to organize several other ones. One big workshop should be on astrophysics and machine learning and other workshops. And each time the goal is really to have a cross-disciplinary workshop with general teams, not necessarily focused on a single application, to have also several disciplines that will interact in each workshop. So basically, if you're thinking about organizing a series of workshops that could fit into a semester long in France, it's not in Paris, once again, please come to us. maybe you send us an email to me or Amanda with a short description, and then from this we'll go forward. We'll organize a meeting between you and the board to discuss what we can offer. So really we are here to help you. It's only take-home message. We will also try to organize smaller events, typically workshop and hackathon, also targeting students. So the goal is also to promote education, and also all sorts of smaller scale activities, such that, of course, a visiting professor will have fellows of the center that will be visiting France from abroad, and also projects that require some engineering time. So if you have some well-planned projects with the code development in AI, you can come to us, and we'll also discuss how we could help you to fund this type of projects. And the last things to just to mention, we are also looking forward activities, as I say, on teachings. It could be a small workshop dedicated to undergrad or graduate students. Once again, comes to us. And also the last but not least, we will also try to develop outreach activities to the general audience. Could be to young pupils, to teachers, and more generally to explain AI and its impact in society to a broader audience. Okay, I spoke fast, but I think you get the message. So please come to me, drop me an email. It's very informal, and then we can discuss. And yes, maybe I could mention that the other sponsor is Share CFM, that is funding part of the workshop, and Julio is the representative and the director, of this share. So if you want to know more about CFM, you can come to him. And don't miss the colloquium, which is organized by CFM at 11:30, just a few blocks away in Salle Jaurès.
The name of the, on behalf of the organizers, ASSAI and the Share CFM for the funding. It was really easy to organize. We can, especially with Marylou, who is very efficient. So she did a lot of work. Amanda also. Yeah, I was about to say Amanda also was really efficient in organizing practical aspects, and it was a pleasure to work with all this team. I think we can start now the scientific part. Yep. Okay. So Marylou will give the first talk today. Okay, so Marylou will give a talk about enhanced sampling with adaptive MCMC powered by generative models. So, please.
Everyone. So yes, today I guess I will start the day where we will be discussing more about generative models, and I think it's another part of the collaboration that we can imagine between machine learning and sampling. And I will discuss a bit broad ideas about how they can help each other. And of course then part of the work I've been doing, so in particular with Grant Roscoff and Eric van den Eyden during my postdoc in New York, but also now with Eric Moline in École Polytechnique and Louis Greniot, my PhD student who is in the room. And also some applications with collaborators, for example in molecular dynamics, with collaborators from the University of Antioquia in Colombia, or with cosmologists in Flatiron. Okay, so just to set the stage, I mean, I'm sure everyone will be happy with the motivation that we'd like to study high-dimensional probabilistic models, and it might be for two reasons that we already, at least for two reasons that we already discussed yesterday. It might be that the physics is telling us that we have a certain distribution of the physical state we are interested in. It might be that it's the Boltzmann distribution, or it might be a quantum mechanics wave function. And based on this Boltzmann distribution, we might be interested in the different states of the alanine peptides. The star, I would say, of yesterday is back on the slide. And then it might be this, or it might be that actually we are observational physicists or experimental scientists, and we observe data. This is my big D. And we want to fit models to this data. And so to quantify the uncertainty, we are going to formulate a posterior distribution on the parameter given the data that we observe. And just the little example I had here for my collaborators doing astrophysics is that you might have, say, observations of the radial velocity of a star exoplanet system, which you observe at different times. But of course, you observe at a limited amount of different times because the observational cost is very large. And so once you have those radial velocity points, you know you have a periodic signals that must explain them. But actually, you can see that you have all those gray lines that are different periodic signals that could explain the observations. And what you want to know is what are the good parameters, so of maybe the good period and the good shift and the good amplitude of these periodic signals, because then you can infer something about the physics of the star exoplanet systems. So just a few examples. And of course, so in those cases where we know the target distribution, typically up to a normalization constant, we are still left with the problem of computing observables from it, which are typically expectations, which we will resolve using Monte Carlo methods. So here I'm going fast because I'm assuming this audience is really familiar with those ideas. But okay, so to have then the next step is to switch from Monte Carlo methods, which would call for IID samples from the target distribution, to Markov chain Monte Carlo as a method to try to obtain those samples that asymptotically will be distributed like the distribution we are interested in, and which, by the way, maybe I should stop to fix notations, because for me they are very familiar, but for you, just to make sure that what I'm calling the target distribution will be a rho, I mean the density will be rho, x will be always the state of the system or the parameters I want to sample, and the energy, or the negative log likelihood, whichever language you prefer, will be denoted by U. Okay, so I want to design those transition kernels that I denote by pi, how to go from xt to xt plus 1 probabilistically, such that in the long run, I'm actually sampling from this target rho of x. And okay, and just again, eventually, I will come back to this sampler, so this is why I just wanted to put it back on a slide. One way of doing it is to use the very famous Metropolis Hastings sampler, where you propose with a certain kernel, which now I called rho index p for proposal, and then you accept reject at each of the iteration, whether or not you should visit the next state that was proposed by your density. And if you don't accept, you stay where you were. And if you repeat this procedure, you eventually, provably under a few conditions, I'm not going to enter to the detail now, you actually sample the target distribution. Okay, so just, I mean, if we take a simple 2D example to fix the ideas, such that this so-called Muller-Brown potential, where here I have the high density regions that are in lighter colors. And if we run a Gaussian random walk, for example, from here, little by little, we are going to accept the steps that are going to lead us towards high density regions. Okay, but of course, what are the challenges of the problem stated in this manner is a problem of decorrelation time and time to convergence, because of course, if I just take this image I had just shown you, which I had run for 100 steps, well, if I continue running it for 10,000 steps, I will not have visited any other high density region, except for a very rare fluctuation that would have put me in another basin. So it will work, but will it work, and will it in finite amount of time? I mean, yesterday we've heard a lot about strategies to try to use short runs, and here we again just restate the problem of why short runs a priori may not tell us everything about the system, and why we need to be smart. So this comes, of course, from energy barriers, and we know that for example, increasing the size of our typical steps proposed, which would be the case in this Gaussian proposal if we increase the covariance of the Gaussian we used to propose, is not going to lead us anywhere neither, because then we will have a trade-off between the size of the move and the acceptance of those moves. So we can try to shoot further away in the landscape, but then we will always shoot, we will most of the time shoot outside of any region of interest, and so this is not the way to explore further. And of course, this has been a really short introduction on those challenges, and there are many propositions and enormous amounts of literature written on how to do better than this Gaussian random walk, starting with just using gradient information with Langevin dynamics or Hamiltonian Monte Carlo. And of course, among many others, also we can think of sequential Monte Carlo methods or annual importance sampling, which will gradually approach the targets and at the price of maybe a higher computational cost, cover the space by targeting from high temperature to lower temperature and exploring little by little. So, okay, this, introduction was just to fix the ideas of the context, and I'm sure it's familiar to many of you. Now, what I want to discuss today is what can we gain from the possibility of using something that is generative modeling, which were developed in the machine learning literature with the goal of doing unsupervised learning. So let me give you a representation of what we could call a general generative model nowadays in the machine learning literature. The idea is that you are going to build a density that represents some data of your interest in the following way. So you are going to give yourself a simple density, which I can call the Bayes distribution. And this Bayes distribution will typically be Gaussian, something you can sample easily, something you can compute the density of. And then you are going to learn a parametric transformation. So this is what I'm calling my T theta, that typically involves neural networks. And so theta standing for the value of the parameters. And this transformation is going to give you the ability to transform any draw of the Gaussian into the structured data of your interest. So let's say that you trained this transformation T theta, so you selected the value of the parameter theta by looking at images of dogs. Then it means that each time you are going to sample a new draw from the Gaussian, if your training was successful, you expect that you will be able to produce a new image of a dog. Okay, and so, seemingly what you did is transform a simple transformation in a possibly very complicated density, because if you think about what would be the density modeling images of dogs in R to the number of pixels of this image, it's probably very structured, very specific. And seemingly, this is something that is possible. And here, just a point of vocabulary, I will call this distribution, so formulated in this way, rho theta of x, the push-forward distribution that is therefore defined by my learning process. So, okay, it looks like there's an opportunity here, could we learn distributions parameterized in this way to be surrogate models for the complicated distribution, which would be our target to sample. So maybe rho star is the one, is the distribution that comes from thinking about a force field on some molecules, and you would like to sample it or get some information from it. Could you try to get rho theta such that it's close to rho star in some way, and become useful to your sampling problems? Well, to this goal, one particularly interesting types of model, which I'm not going to enter into the detail of right now, but I'm very happy to discuss offline, are normalizing flows. And normalizing flows is just one of specific type of such construction in which we impose that the map T of theta is invertible. And in such way, it means that not only we can evaluate the density at the base of our generative models, the one where we draw the simple realizations before transforming them, but we can also, through the change of variable formula, compute explicitly the value of the push-forward distribution. So, okay, so right now I'm just telling you that they have these properties. In a few minutes, it will be very obvious why we need those properties. And then that's where I'm entering in the art of the topic of how could we try to use those generative models in order to enhance sampling. And at least when I started, there was two big questions that we had to answer. The first one is how do we go around the chicken and egg problem? So once more, one of those chicken and egg problems that we also heard a lot yesterday about in learning reaction coordinates in order to sample from data that you get when you have reaction coordinates. So here it's a bit of the same story. How do we train those generative models to obtain better sample if we don't have the training data, which would be the samples themselves? So we have the same question here. And the second question is, of course, famously, deep learning is not really explainable, and it's really hard to obtain guarantees in performance in deep learning. So how we circumvent this uncertainty in the performance to obtain some guarantees on the sample. So this one is actually rather easy to tackle. This other one, I think, took multiple iterations in the literature to be explored. So So I've been working on this for a couple of years now, but actually many people have started to work on those ideas. And so I'd like to start with the start of the story, where the first idea to solve the chicken and egg problem, in which eventually we want to obtain a modeled density with the deep generative model that resembles the target distribution. The traditional way to promote this resemblance between the two would be to do what we call maximum likelihood. Which is one very reasonable objective in statistical inference, in which we would maximize the likelihood of the data, but at the price of having training data, which in our case would mean that we have samples from the target rho star, and which at first is not really an achievable objective. So the first idea, which was still quite natural, was to reverse the KL divergence, because this could also be seen as a Kullback-Leibler divergence. But anyway, look at this loss function, which is a measure of the divergence between two distributions, and which in its expression can be expressed as an expectation over rho theta of x, meaning over the density defined by the generative models, which is something that we can easily sample from, and so an objective that we can easily estimate simply by taking samples from rho theta of x. So yes, good idea. Let's see what happens if we do that by trying to target a very simple example, which is this mixture of Gaussian. Right, so I have this mixture of Gaussian. I'd like to learn a model rho theta that resembles this rho star, and I will do that by minimizing such divergence. And I'm going to start here. So the gray lines correspond to my targets, and the blue corresponds to my rho theta. And I put an index t because I'm going to train by doing some gradient descent on this objective. So I'm going to iteratively refine my model in blue in a way that is, I'm trying to have it fit this target. And what I'm putting on top, the dots, correspond to actually the samples I'm getting from this rho theta in order to evaluate this objective. So it's the way I actually compute this by making an empirical sum over the blue points. And so if I start from this random initialization, if you want, where, okay, at first my rho theta of t is here, and I run a gradient descent, what I'm going to see in this case is what we call mode collapse. So what does mode collapse means? It means that the model is going to concentrate in one of the modes. And here we can understand that it has no idea, I mean, there is no reason to find the other modes, because in the end, in the full learning process, it was never able to detect that something else interesting was happening in the space, since it was only using points from itself in order to evaluate the loss. So good idea, and sometimes, I mean, I'm not entirely fair to people who actually made this work in some cases, but it also can suffer problems, and in particular, it's sensitive to mode collapse. So second idea, and arguably very important paper in the field, is what Frank Noe and his group in Berlin did in their paper called the Boltzmann generator. And the idea was to keep this variational inference, so maybe I did not name it, but the first loss function I was discussing with the KL that we can estimate is this variational inference loss. So this is exactly the same as the last slide. And the idea was to add some training data that will correspond to short runs of molecular dynamics, because this group was interested in molecular systems. So what they would put is also a proxy of the maximum likelihood, which would correspond to estimated dislog likelihood on a small set coming from molecular dynamics. So that was their first idea, and they called it training by energy plus training by data, because here you have the energy of the target rho star that enters in your loss function, and here you use the data. And okay, so they said they argued for a combined loss, and they also argued that once the rho theta was trained to resemble the rho star, then we could correct samples simply by doing importance sampling, so computing the importance weights and estimated any of the expectation we are interested in by a weighted sum. And remark that here we need the fact that this rho theta can be evaluated so both in the training loss and both in the fact that we can correct after training by computing the importance weights. And by doing this, so they had, again, this combined situation where they had their surrogate model, so which is schematized in this way, because I remind you that typically you have a simple Gaussian distribution which you transform to generate the rho theta distribution, and then with the importance weights you reweight to try to target the Boltzmann distribution. And they managed to have nice results on quite large systems with this approach. Yet maybe one question that is left unresolved is how much data is enough data in this scheme where you need training data in order to have the training going on. So the third idea we investigated was to look at adaptive MCMC methods. So these adaptive MCMC methods have been around for around more than 20 years now. And the idea is that you are going to learn from the chains you are propagating in order to adapt the kernel of the Markov chain. So it started with Arjo and collaborators who were adapting the covariance of the Gaussian matrix they were using in Gaussian random walks. And this is the deep learning version of this simple idea of doing adaptive MCMC, where what we are going to do is actually learn with the normalizing flow. So these types of generative models, I can write the rho theta off and sample easily. So we are going to learn the proposal distribution in a Metropolis Hastings sampler. So here, I'm sorry I put the algorithm on the slide, but the concepts are relatively easy. It's really just having a certain number of chains and looping over the chains to propagate an MCMC. And this is really just Metropolis Hastings with the proposal given by the deep generative model. And from time to time, stop to be propagating this MCMC to collect all the states you have seen in the chain to take a gradient step of maximum likelihood in the training of the row theta. So this is just what this line means, is just that I'm adjusting the parameters of the flow theta according to the direction of maximum likelihood using the MCMC chains I've been propagating as data. So MCMC correction, if you want, of the flow, and improvement of the surrogates as I go. So this is the two different steps of this adaptive MCMC. Okay, so if I just, again, use simple examples, which I think are really helpful in fixing the ideas of what's going on in the algorithms, and I give myself the same target density. Of course, if I was only to run a local sampler, and that I was, for example, initializing MALA, which is the Metropolis adjusted version of Langevin dynamics, I would collect well data in each of the modes. But if I were to look back at the data that is generated by this MCMC chain, of course, since I don't have mixing in between the two, I will never realize that one of the two modes was twice as likely as the other one, right? So unless I actually initialize the chains to have exactly the right ratio in each of the modes, I'm not going to get this simple information, yet crucial, about the target distribution. Now with the methods of the adaptive MCMC leveraging the power of deep generative model, what's going to happen is, again, I'm going to initialize two chains at the red stars in each of the modes, and I'm going to propagate the MCMC chains such that I'm using the data to train my surrogate model, which again is this blue density, which at first knows nothing about the targets, but little by little is going to improve as I'm propagating the MCMC chain. So in gray, you have the MCMC chains, and what we can see is that as the blue density is starting to cover the different modes, then the chain is able to mix in between the modes because the proposal, which distribution which corresponds to the blue density, is starting to match the targets. So in the Metropolis Hastings acceptance accept reject criteria, it's starting to see that there are good locations that are proposed, and so on and so forth. And so in a virtuous circle, if you want, the system learns and mixes. So if we look precisely at the final learned density, so this is the final row theta that my generative model has learned. It's not perfect, but it definitely has an idea of where are the interesting modes and even what are the relative weights of those different modes. So far, so good? Yes. But of course, there is no free lunch. If I start only one worker in my MCMC chain in only one of the modes, then I'm going to suffer from the same mode collapse. Well, not exactly the same, because this likelihood is going to cover more the one mode I got, but I will have, in the same way, completely forgotten. I mean, I've never learned about one place in the landscape that had some interesting features. So, well, it means that there is no mode discovery. So, okay, and if I just put that back on a workflow, because maybe this is nicer than the algorithm. The idea is to propagate the MCMC chains with, from time to time, an extraction of the data of the MCMC chain to train the normalizing flow, which improves the parts of my kernel that corresponds to non-local sampling with the normalizing flow proposal. So here, maybe I didn't insist too much on the fact that the sampling from the normalizing flow was non-local, but the idea is really that when we propose with the flow, there is no conditioning on xt. It's really xt plus 1 that is proposed from anywhere in the distribution that has been sampled by, that has been modeled by the normalizing flow, which means that the only correlations in the MCMC chain you get come from the rejection, from the times that you have rejected the chains, the move that was proposed by the normalizing flow. So, okay, and here you can see that you have jumps that go all the way because you really propose non-locally anywhere there is mass in the blue density. Okay, so again, this is this inherits from all the literature on adaptive MCMCs. And something I also did not yet insist on is the fact that we believe that it's also important to keep some local parts to the kernel. So we are actually alternating between the non-local normalizing flow proposal and a local sampler. And maybe I can try to give you some intuition on. So how much time do I still have? Is it, what time do we?
Next talk is at 10.
So best chairman. Okay, so now in face with this simple idea, there are different questions we can ask. So actually, adaptive MCMC methods are non-Markovian intrinsically because we are going to have a kernel which itself depends on what we have seen in the chains before. So there are questions of convergence of those algorithms. And also, I mean, just that's maybe a side note, so I may skip this part, but I could try to give intuition on why we believe we should keep a local sampler. But just for the people who like these types of analysis in the room, it's possible to write an ergodicity theory for those adaptive MCMCs, and interestingly, we can show that for this training that relies on adapting through a gradient descent surrogate model rho theta, this analysis can go through. And if I just summarize in one slide a bit the key elements of this analysis, we have so an independent proposal. So again, this means that we have a purely global way of proposing, which is not conditioned on the last step of the chains. And this category of independent metropolis Hastings sampler is much easier to analyze than the local ones. And then we have, okay, the metropolis Hastings kernel that has the acceptance part and the rejection part where we stay where we were. And then we need two assumptions for an ergodicity theorem to be written. We need the sequence to have diminishing adaptations, which means that we need the transition kernel to stop adapting eventually, if you want. So here it's a condition in total variation of the difference between two consecutive adapted kernels. So here theta of n corresponds to the fact that we are at iteration n seeing the parameters evolve due to the gradient descent, which is not a big assumption for our SGD training, because we can always, for example, have a scheme where we take the learning rate to 0. But probably the most stringent condition is the one of having containment, which basically is going to have a bound on the ratio of the target density and the proposal density that needs to be uniform on the space and for all the values of the parameters, and in particular at initialization. So this is where things get a bit how should I say, disappointing, because in the end we need to have things that are really well conditioned in order to be able to write that the chain is going to be ergodic with respect to the target distribution. So it can be written, but in practice this never happens. So how do we really make, okay, it's, I think it would be nice to have ways of refining this, so if people are interested, I'm happy to discuss about this. Okay, so maybe I will skip the local parts of the kernel since I don't want to take too much of the time. But if I just discuss rapidly first applications of these ideas, and I wanted to start with the one that maybe relates to a lot of things that have been discussed yesterday, is using it to try to sample molecular systems, where here the target density is given actually by a quantum force field, so density functional theory. And the system we are currently looking at with Ana Molina Taborda, Olga Lopez Acevedo, and Pilar Cosio are these 6 atoms of silver, which you can show have 2 stable isomers. So, and this is at room temperature. And of course, okay, we can use a local sampler, which is molecular dynamics, to look at the oscillation of one of these isomers in his own basins. But then with the adaptive MCMC and a normalizing flow, we are able to create jumps in between the 2 isomers. So this is a vision in collective variables of those 2 isomers with a free energy surface which was computed by metadynamics. And here you have the chain in orange that is oscillating between the 2 basins. So importantly, here we have an MCMC chain which we believe can equilibrate between the 2 basins, but we have no information about what is happening in between the dynamics. So I guess it's both an advantage and a drawback. So for example, Ruta yesterday was telling us about how to learn with information only in the 2 basins some classification coordinates that will give us some reaction paths. So sometimes it's nice not to have to worry about what's in the middle, but maybe it's also disappointing to physicists and chemists that we don't really know about how this process happens. So I don't know. I mean, it's a method which is here, and I'm happy to discuss what everybody thinks about it. Yes.
Molecular dynamics is Hamiltonian dynamics or non-Hamiltonian dynamics?
I don't know. It's I think it's no, I think it's a Langevin dynamics, but I'm to be honest, Anna is running the experiments and I don't know. Okay, and so one last thing to mention. I mean, one other important, I think, class of applications to mention here is the one of high-dimensional field models. So when I'm looking at 6 atoms of clusters, I have 6 times 3, so 18 dimension, which is fairly large, but not really huge. So something we wanted also to test on is some should I say, toy model in a sampling problem in statistical mechanics, which can become arbitrarily difficult in high dimension and also is experiencing phase transition, is this 5-4 model, where we have a random field. So before discretization, ultimately we will discretize. It's actually a continuous function on 0, 1, and it has an energy functional that has local potential, biasing to be -1 or 1, and a coupling term that biases the field not to change too much on neighboring sites, and which gives typical realizations like this. So here you have 4 different realizations. They go from, and we have boundary conditions, so they go from 0 to 0, either going through 1 or through -1 with a certain scale of fluctuations. And again, this actually can be sampled quite efficiently with this method. We have acceptance during the MCMC iteration, so the training that is going up as the normalizing flow is refining itself towards reaching 60% acceptance, even if we are, for example, in 100 dimension. And we have fast mixing, as we have 10 different realization of the field, so which are jumping from one mode to the next really efficiently in this plot. So this is working. I'm also taking time now to just discuss rapidly this, because this has been really a toy model, and I think Ryan will tell us about related model later today with his work with Fiala, who will join us tomorrow. And also Stéphane will maybe discuss similar, similar models with maybe different methods, and importantly, maybe methods that incorporate some of the knowledge of the physics. So here, in our case, maybe I'm running out of time to actually discuss this, but maybe if I'm just telling the moral is that we were able to incorporate some physics in the base distribution, which was key to success, and we will hear more about this, I believe, from both of the other speakers who will discuss about this, and this is where I wanted to end on whether or not these methods can scale. And there has been a really nice paper by the group of Del Debbio that look at this 5-4 model, but this time in 2 dimensions. Just if I make it short, this model, if we look at now in 2 dimensions, you have spins that are up or down, so up will be white, and down will be black, and here it's a continuous model, so you have gray in between. And you have critical temperature, so below which you have one polarization that is preferred, and above which things are less clear. And what they did in their systematic study was to look at the acceptance of these types of algorithms, so how often can a normalizing flow that is trained as well as possible create configurations that will be accepted by Monte Carlo chains, so will be physically likely. And what they showed is that this acceptance, so here you have the size of the system, is going down with the size of the system, which quite irreversibly, and in particular at the phase transition, because here you have the temperature and of the phase transition. And one way of understanding that this has to happen is the fact that if we have extensible energies, then if we add degrees of freedom all the time, eventually we are going to have a scaling of the acceptance that is exponentially bad in the dimension. And so again, I think techniques of separations of scales that Stéphane will tell us about could be one solution to this type of problems. But okay, if I just wanted to mention that this probably is one of the biggest challenges for this approach. And if I just conclude here, it seems that there are a lot of opportunities, but also challenges, which in particular seem to suggest that we should really be joining forces with traditional approach and also incorporating as much physics as we can in the systems. And finally, there are some softwares which some of them I'm involved in, and some that are a bit more sophisticated on sequential MCMCs that are available online if you are intrigued and you would like to play with those methods. And with this, I would like to thank you for your attention.
Thank you very much, Marylou. Questions in the audience? Yes. Let me come to you.
In your experience playing with these things, do you ever notice the formation of spurious modes where you're not sampling?
What do you mean the formation of spurious modes? You mean that the flow will learn something that is actually not a mode?
Yeah, so that happens, for example, in VMC with neural networks. You'll get modes that form where you're not sampling because it has no reason not to do that.
So here, no, because that's because of I think an inductive bias of the method. So the normalizing flow works that it has usually a one unimodal Gaussian in the base, and it's going to try to tear apart this multimodal Gaussian in matching the modes you are showing data on. So it's more adversarial to creating a node. Yeah. So I think that's the reason. Whereas if you are using just an energy surface, then things could go. But here you have these constraints. That's
Yeah, very nice talk, so thanks. I had 2 small questions. One to clarify. So the normalizing flow is proposing a non-local move, and then you accept or reject with the
yes.
MCMC to get the density right. Okay, that is clear. I was wondering what the meaning is of this, almost this bridge, this tunnel that
Yeah.
you actually create during the normalizing flow. It looked like it was still there in the final learned density. At
Yes.
least you see it very vaguely.
Yeah.
And does it eventually completely disappear, or is it always there? And what does it really signify?
Yeah, so it's. I think I always get this question, so maybe I should just start just explaining from scratch. But it makes total sense. I guess I had the same question when I started. So again, what is it? It's exactly what I was describing to John. That when you have this process of separating the mass, and here we have the constraint that we are only using an invertible transformation, so it cannot change the topology. So there will always be a link in between the different modes. And here, what's interesting, and that's maybe something that can be solved, and I'm happy to. I mean, there are ways of changing that, but the way we are transforming this unimodal Gaussian in this two-modal Gaussian is through a transformation that is really not much constraint. We only constrain it that eventually it looks like these two modes. But for example, we could think of ideas from optimal transports that will, this doesn't look very efficient to go from here to here, right? So probably if we have objectives of making these mappings that are a bit more strict, then we could have that we are changing that more constraint. So here, if you want it, this is my spurious, this is my spurious thing. So I'm not too worried because for the percentage of the whole mass, is not really significant. Maybe sometimes I will propose, I will reject, but yeah, that's what it is.
Yeah, thank you for the talk. You're using this very simplified distribution in light and space, this Gaussian. Is there a strong argument against using, for example, high temperature configurations or so, which have are a bit more physics informed?
So yes, so no, well. So basically, I didn't. There are papers who actually. Okay. The first argument not to is that even if the state is simpler to sample in high temperature, it will not be directly sampleable as we can do here and have something that is purely non-local. However, I think you're totally right that what you could do is try to learn a map that maps high temperature to lower temperature. And this is something that is done in papers. Here, did I... Yeah, so yeah, we can discuss because some papers have learned even a series of flows that if you want follow the annealing schemes, so to target little by little the different temperature, so either in temperature or in Bayesian models. You have also, so Arnaud Doucet, who is I think not here yet, is going to also discuss that in the sequential Monte Carlo world where you just take the prior as your high temperature and you slowly by slowly map it to your posterior. So it's I would say the annealing of Bayesian inference. So yes, that's been done and that's possible.
Do you need to know a priori all points of concentration of measure, or algorithm can find them automatically as it progresses?
Yeah, so in this simple version I showed you, no, there is no reason you will find something that you haven't put in the initialization of your workers. However, there are people who have written this algorithm by, also using some annealing, and in which case you can do it. So I think, and this is something I'm happy to discuss also offline, I think you can do it so little by little, creating a lot of models, but you could also train one model just annealing the targets along the training, and probably this will be the cheapest way of finding modes. But okay, I don't know, to be discussed. If you're interested, I'm happy to discuss.
Thank you.
Last question.
Yes. I was thinking, so the last problem that you said, so the case to use this method in the case of big systems, so many degrees of freedom. So it looks like in that case, to solve the problem of metastability in this case, so even without metastability, there is this problem. So somehow it seems that you have to introduce back some kind of locality, as you said. But then if you introduce back the locality, then you do not have the big jump. So maybe indeed one way to go is introduce locality and multi-scale at the same time.
Yeah.
That could really. I mean, it's otherwise. It seems that there are difficult. I mean, it's otherwise.
Yeah. No, I totally agree. I mean, this is I mean, this is me actually trying to have you and Stefan do this project.
Okay, let's thank again Marylou for this nice talk. For the next talk, which will be given by Alain Durmus from École Polytechnique, and he will talk about invertible flow non-equilibrium sampling. Thank you, Alain.
Thank you very much for that invite me to this very nice workshop and this. And so I changed a bit my. Je préfère pas pour les autres. I changed my talk finally because I saw that this one will be more appropriate for this workshop, and which really in fact because in fact the idea really come from a physics paper, and so I'm quite happy to hear about the algorithm we developed here. So this paper was in collaboration with a bunch of people, and so here all of them are here, and so let's start quickly by some introduction and motivation. But in fact, this introduction will follow quite closely what Marylou already done, but maybe from another perspective, more from a generative modeling perspective compared to Marylou. So here, what I'm interested in, and all of you guys, I think, also are to sample from a probability distribution, non-optimative constants, because, so I'm mainly interested in Bayesian inference and application in machine learning, such as generative model or inference of with missing data. But typically in this problem and in a problem in physics I showed yesterday, you want to sample from from some distribution, optimum normalizing constant, or even just compute this normalizing constant, also called evidence, or more generally compute integral as Marylou show in this talk. Okay. So here are a basic generative model, okay, which is a deep Latent Gaussian model, because okay, so it's a very simple one. So in fact, here what I have some observation y, so here, which I want to get new sample, which does not look like the original one. You hope. So for this, you take some statistical model. You assume that okay, y is equals to f of g theta z and w, where g theta z is some transformation parameterized by theta of a very nice distribution you can sample from. So here I take as Marylou a Gaussian distribution, but okay, since I don't necessarily use normalizing flow, this Gaussian distribution is can be of different dimensions. That's the image space of g theta. For and y are some adding randomness here, and f is a link function, just to gather all the things to get a new observation y. Okay. So popular function for g theta. So here in GAN, g theta corresponds to the generator, and for variational autoencoder, it corresponds to decoder. Okay. So now, okay, you have your statistical model, but you still need to infer the best parameter theta based on your data. And for this, and so yes, first, well, a very simple example to put into context the general model I presented you before. So here I consider the binary MNIST dataset, where my observation y consists of pixels, 0, which are binarized. So here I have g pixel, okay, y1 to yp, which belongs to 0, 1. And here I assume that in a very simple model, that's okay, conditionally to my random variable z, okay, my hidden random variable z. Y1 to yp, conditionally to z, are IID Bernoulli with parameter g theta z, okay, and g theta z is a function there, and here I take for the g's component of y, the g's component of g theta. Okay, so here, in fact, what I expect is that g theta is a function which gives me a Gaussian, and which from a Gaussian gives me some parameter of some Bernoulli random variable. Okay, and that's it. So now, okay, that I specify my statistical model, I can write the likelihood, but okay, here comes the problem. That's my likelihood. Okay, p theta y is not that simple because it is an untractable integral. Okay, because here, okay, p theta y consists just of the marginal of p theta y and z, but p theta y and z is okay the product of p theta y given z rho z z using your favorite Bayes formula. And here, okay, since you marginalized, okay, you cannot have access easily to the marginal likelihood. Okay, but still, okay, if you believe in maximum likelihood estimation, what you would like is still to try to maximize this function, okay, as a function of theta given your observation y, meaning that you would like to find the best parameter which fits your data, meaning that okay, once you find theta star which maximize the empirical likelihood as stated to y1 to yn. And so, okay, again, the main issue is that okay, log of p theta y is not tractable, and the number of parameters d can be quite large. Okay, and as the number of observations, so what you should do, what you think of, if you have already done some machine learning, you still think about stochastic gradient descent. Okay, and you can use stochastic gradient descent even in the case where your integral is not tractable using the Fisher identity, because okay, here I can write the gradient of my objective, log of theta y. Okay, you just use the limit convergence to get the gradient in the integral. Okay, make appear in fact now the marginal, the condition, make appear artificially in fact the joint likelihood of y and z here, and so I end up with a gradient of the log of the joint, which I have access, times the posterior distribution of my hidden variable given my observation. Okay. So here, I have somehow a an integral form for my gradient. So I think about that I could use stochastic gradient descent, but still, a problem persists, meaning that here, if I want to use stochastic gradient descent, I need to sample from my posterior here p theta z and y. Okay, and so here comes MCMC or your favorite MCMC algorithm or Monte Carlo method. Okay, so here my objective, I think I motivate a bit maybe my the setting. So here I want to sample from a target density pi. Okay, just for notation, where pi has a product form, else time rho. So here rho, be careful, is not my target as Marylou. Rho is here in fact plays a role of my prior, or the distribution of my latent variable for generative models, and L plays the role of my likelihood, or my posterior distribution. And I assume this this product term because I will use in fact this structure in the method I will present to you. And my goal is to sample from pi, try to efficiently compute the normalizing constants or compute integral with respect to pi. And I will start with this problem, to compute the normalizing constants first, because in fact all the methods which I will derive in the sequel will be based on the method I will show to you about how to try to approximate this normalizing constant. Okay, so here comes in fact the Neo estimator, which is the estimator which we suggest to compute the normalizing constant. So here, I will call you the basic Monte Carlo estimator to try to approximate z. Here I can just use the empirical average of the L of xi, where xi are ID sample from rho, because I have assumed some product form for my target pi. And the hat is unbiased. It's quite easy. But here, the main idea is that, can we try not to use some transformation, smooth transformation of my based my reference distribution rho, which I assume I can sample from. For example, in Bayesian inference, you can assume that you sample from the prior, but the prior in general known. Or in generative model, it is really the noise you generate from your hidden variables. So here I really assume that I can sample from rho, but still, can I use some transformation by a map T of rho in modifying a little bit this estimator and trying to reduce its variance. So here are the first idea, and for this I assume, and I will try to slightly relax this assumption, but the push forward measure of rho by T is equals to rho. Meaning that if I consider a random variable x distributed according to rho, T applied to this random variable is still distributed according to rho. And so now, based on this assumption, in fact, I can use the orbits by T of some sample xi, in a new estimator and combine it using a convex combination. And okay, so using this assumption, I can consider this new estimator here of my normalizing constant. So here it's some empirical average of convex combination of my likelihood applied to the orbits of associated with some sample from Rho. Okay, so here it is quite easy that, okay, since I assume that my transformation preserves my reference measure Rho, it is straightforward to see that this new estimator is still unbiased. And an easy Jensen inequality tells us that, in fact, the variance is still better. Okay, but still, okay, we are not quite. It is quite a strong condition at the end to assume that T preserves Rho, and so the main idea is that, okay, can we try to bypass this condition and still have an unbiased estimator for the normalizing constant, but here, okay, using some kind of general T. Okay. So for this, okay, now I consider a general transformation T, but okay, here I make somehow still an assumption, a stronger assumption than before. I don't think so, but so here I assume that C is a C1 diffeomorphism from RD to RD, where RD is the state space where my target is. Okay, and from this map, okay, I can consider the push forward measure of Rho by the case iterate of T, and using your favorite change of variables, you end up that Rho k here. Since I assume that Rho has a density with respect to the Lebesgue measure, has also a density given by Rho applied to T minus k x, the Jacobian of the minus k iterate of T x. Okay. So now, okay, I have a family of distribution indexed by k related to the case iteration to my map T. And based on this sequence of distribution, I can consider this one, okay, which will be at the core of the method we develop, which is a what we call a non-equivalent measure. So here, Rho T of x is a convex combination of Rho k x. Okay, so it is still a probability measure with respect to the Lebesgue measure. Okay, and so here we can use, in fact, artificially Rho T, okay, to make appears, to try to generalize, in fact, the construction I gave you before. And the K identity is there. So here we write for any test function f, we can write any integral of f with respect to Rho. Here I artificially introduce Rho T. Okay. Here I just write the expression of Rho T in the integral and intervert the sum and the integral. Okay. And here, what I can, from this expression, okay, I can observe that, in fact, rearranging term and putting the sum in the integral, I can, in fact, rewrite, okay, the final integral as integral still with respect to Rho, okay, but some sum over the orbits of my transformation T, and with some weight wk. But here, okay, compared to to the case where T, in fact, preserved Rho, this time, okay, the weight will depend on my position x. Okay, and that's really the core observation there. Is that okay? We can still, in fact, consider some kind of unbiased estimator for the normalizing constants here, but here we need to consider some weight, which will depend which will not simply be convex combination var pk, as the case where T preserves Rho, but will depend on x and will explicitly depends on the sequence of distribution Rho k I defined you before. Okay. So here you can really see, okay, that this expression allows you, in fact, to introduce a generalization of the importance sampling estimator using orbits of your transformation, but with weights which now depends on your states. And so the new estimator, okay, which we call NEO for the normalizing constants here, is exactly as the one I presented you before in the case where T preserves rho, but this time, okay, I introduce the weights are really the weight I introduce you here, okay, and okay, it needs to be computed, but okay, it's everything is explicit. Okay. And still, okay, based on this expression, okay, you can ensure that this new estimator is unbiased. Okay. So here is just a quick summary. Okay, that's okay. How to compute the estimator, the NEO estimator. That's okay. You sample x1 to n from your reference measure rho, which will be some particle. You make evolve your particle, okay, according to your transformation T. Okay, so here you consider all the orbits associated with your particle x, with each particle xi. Here you compute the weights associated with each particle, and okay, now okay, you can consider the empirical average of the. Sorry, here it should be some infinite sum still, but so here you have the estimator of the integral of f for one particle, okay, and using all the orbits. So here, okay, you can compute based on this algorithm. You can also compute easily some integral with respect to pi, just putting for f instead of l, g times l, okay. And okay, just for in practice, of course, you cannot consider infinite convex weights var pk. You should in fact truncate them for some threshold big K. Okay. So what in fact this method comes from? So here we take inspiration from this paper by Rotzkopf and Van den Engden, but in fact which presents this method in continuous time. Okay. Everything was continuous time, and even the proof was based on some continuous time result, which we are not aware. And here, okay, and so in their method, okay, since they consider only continuous time, they had some discretization error, whereas here, in fact, we are exact and unbiased. Okay. So I present you some important sampling, some kind of important sampling estimator based on orbit of some transformation. So I can also, if you are, I think if you already done some Monte Carlo, you can also think about self-normalized important sampling, where this time, okay, you combine in fact the estimator I showed you before with the estimator of the normalizing constant to compute some integral of g with respect to pi. Okay, so here this time I can consider this new estimator, okay, for this quantity g var p n of g as, okay, here I identify at the bottom the estimator of the integral of g rho times L gx here. Okay, that's my ugly expression there. Okay, and at the bottom that at var p in fact really corresponds to the normalizing constants of my target pi. And so, okay, if you believe the law of large number, this estimator will converge to my target, to my quantity of interest pi of g. But still, okay, at a finite sample, you obtain a biased estimator, but you still can have some bounds on the bias and the variance. Okay, and okay, here is our very easy calculation to show that in the case where you assume some variance of your estimator, finite variance on your estimator, you can bound the bias by 1 over your number of particles times the variance up to multiplicative numerical constants. So here are the bias and here are the variance. Okay, so here the variance and the bias are scales at the same order, which is the number of particles. And of course, if you assume crazy assumption on the weights, meaning that okay, they are bounded, you can also obtain high probability bounds just applying Hoeffding inequality. Okay. So now comes the choice of my weighted sequence VARPK, okay, which I should use. So here, in fact, we didn't try to we didn't try, in fact, to optimize this sequence, but we could, okay, maybe using adaptive method, which Marylou presented in this talk. But here, okay, what we can wonder is that, okay, which kind of transformation T should we use to obtain good estimator? And for this, we can use this very simple lemma to guide our choice. So here, in fact, the variance of the estimator of the weights of the estimator I presented you before can be bounded, in fact, by the chi-square divergence between pi and the distribution rho t I present you in my previous slide, plus 1. Okay. And what you would like somehow is that your weight, if you believe that your estimator is your proposal in importance sampling are efficient, you expect that your weights are approximately equals to 1, which translates here that, okay, you expect that a good transformation T brings, in fact, that the quantity ET VARP is approximately equals to 1. Okay. And here, you can ensure this by this lemma by ensuring that, okay, pi, the chi-square divergence between pi and rho t are approximately 0. And what it gives, it informs you that, okay, T should bring rho, in fact, to our identity region for for pi, okay, and that's the first constraint. But the other constraint, in fact, which is really computational, is that here I want to compute the weights associated with my estimator. And the weights, in the weights of my estimator, I need to compute the Jacobian of the iterate of my transformation. Okay, and what we want, okay, we want first, okay, that T brings sample from rho to identity region from pi, but we want also that the Jacobian of the iterate of T to be easy to compute. Okay, so here we thought first to maybe using normalizing flow. But okay, it was a pain in the ass to optimize. Okay, so here we just take inspiration again to Van den Hegden and Roscoe's paper, and we use, in fact, conformal Hamiltonian transformation. So what is conformal Hamiltonian systems? So I consider here a potential energy and a kinetic energy. Okay, so here and the Hamiltonian associated with these two quantities. Right? So here, in fact, the potential energy is really the negative likelihood. They correspond to the energy of my targets, associated with my targets. And here, okay, it's some kind of artificial energy which I add to build my Hamiltonian system. Okay. So based on this Hamiltonian, based on the Hamiltonian function, you can consider the conformal Hamiltonian ODE, which is not the traditional Hamiltonian system, because here, in fact, in the Hamiltonian equation, I add a damping factor there, okay, minus gamma pt, which weight, in fact, make my system decelerate in time, so it will stop at some point. And in fact, it will converge. What we expect is that, in fact, it will converge to a minimum of your Hamiltonian function. Okay. And the minimum of the, it will be a stationary point of the gradient of your Hamiltonian function. And okay, stationary point, and if your Hamiltonian function satisfies that it vanish the potential, okay, and it's for the momentum it's simply 0. So more or less, if you look at, in fact, just the position, that what you expect is that, okay, following the conformal Hamiltonian ODE brings you the position to region where the potential is high. Okay, that's more or less your expectation. And here, okay, so are some simulation illustrating the behavior of conformal Hamiltonian dynamics. So here you have the Hamiltonian field, the dissipation field, and here if you combine both of them, you can see that, okay, here you converge to 0, which in fact is the zeros, the minimum of the Hamiltonian, which cause here I simply consider a quadratic potential. So, of course, you cannot have exactly solution to the conformal Hamiltonian dynamics. So you need to use an integrator, and here we consider a symplectic Euler discretization, okay, which in fact can be defined for a step size h as follows. So here one step of my symplectic Euler discretization will first define an update for my momentum at exponential minus h gamma p0 minus h gradient u q0. Okay. So here, in fact, for the first step, it corresponds to integrate explicitly this equation with respect to p for some position q0 fixed. Okay. So that's why, in fact, you have the exponential term there. And now, okay, that's you have fixed the position and follow the Hamiltonian dynamics for the momentum. You can do the same for the position, and so you end up with Q1, which is Q0 plus HP1. Okay. So now, okay, one step of my discretization will define my transformation T, which I consider. So I define TQ0 P0 as Q1 P1. Okay. So be careful. So here I have extended my state space somehow. Okay, so whereas in fact in my previous slide I wanted to consider transformation from RG to RD, but okay, here in fact I can simply consider this transformation for an artificially adding the momentum and discard, okay, in the algorithm the obtained momentum. Okay. So what is nice with this transformation is that, and that's why in fact it was considered, that okay, it is quite easy to show that it is a C1 diffeomorphism as composition of two, and the Jacobian is relatively easy to compute because you have a symplectic scheme here, and the Jacobian of this transformation of Q and P is equals to exponential minus H gamma T. Right. So here are some illustration of this dynamics for different damping factor gamma. So here what we plot in fact the estimation of the variance of the weights for different damping factor gamma, and we compare with this variance with the variance of the crude Monte Carlo estimator at fixed computational budgets. Okay. So here you can see that you have some kind of trade-off, okay, in the choice of the damping factor. So here if you choose, so here the best choice is for gamma equals 1.0, which is in the middle between 0.1 and 2. Because in fact you have some kind of trade-off in the use of conformal Hamiltonian dynamics. Because okay, if you choose gamma, which is too small, okay, in fact, you will not converge quickly to you will converge too slowly to the minimizer of your potential, which in fact you can show here. Okay, you turn around minimizer in a too long period. Whereas, okay, if you take for gamma a too large value, okay, you will converge in fact too fast to the minimizer, and you will not take the time to explore enough the state space. Okay, so here the right trade-off somehow is really to take an in between gamma, and of course, in fact, it should be depend on the potential, as you will see, because here we really have some kind of it is not it is a standard Gaussian, but if you have some correlation, of course, in fact, gamma should you should use different damping factor. So here are some simulations for the estimation of normalizing constant. Okay, so here I want to estimate normalizing constant for distribution in dimension 10, 20, and 45. And for two models, for the first one is 25 mixture of Gaussian, okay, with some mean, okay, mu ij, which are in fact 0 in all components except the first two, for which it is I and G, and some not so well conditioned covariance matrix sigma. So here you can really see that you have some the variance here is very small in the two first components compared to the other. And we also consider the final distribution. Okay, so here, so the name comes from, in fact, the form of this distribution in this marginalization in the first and second components, because you have the form of a funnel. Okay, so here you have some kind of filaments, and okay, it is considered to be a very hard target distribution to sample from. So here are the two models in different dimensions that we consider, and for rho, okay, we start from rho as a Gaussian distribution with a variance sigma square rho, which is equals to 5, okay, to cover, of course, all the modes of our target. Okay. So here are the results, and we compare with the competitor. So for the Gaussian model, okay, we can see that the neo-estimator gives quite efficient results, quite effective result in comparison to other algorithms, such that the crude impedance sampling, the annealed impedance sampling, and this counterpart NES. So here, for the Gaussian case, you can really see that it gives credible result, even in relatively large dimension. And for the final distribution, it also gives quite nice, the best results in comparison to the other one. Okay, so how much time I have? Okay. 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 So I will try to be very, very quick then. So once we have, in fact, a new methodology to compute normalizing constants, we can use, in fact, can try to adapt, in fact, sequential Monte Carlo algorithm to use this particular estimator and design new MCMC algorithm, and that's, in fact, the purpose of this section of my talk, where, in fact, we adapt we adapt CIR and ECIR to using neo-estimators. So first, what is CIR? What is sampling, impedance sampling? So here, I consider some particle. Okay. I consider some particle distributed according to rho, and so based on this particle and the reference measure rho, I can compute some indices, some random index E star, which have a multinomial distribution with weights proportional to L tilde xi, okay, which correspond to some weight, where L tilde xi is in fact my normalizing weights, L of xi divided by the sum of L of xj. And then, I set, based on this index, random index, I said, that my sample, x star, is equal to x of E star. So here, I have a sample which approximates my target distribution pi. Okay, it is not hard to show, but it is biased. Okay, it does not exactly target pi, but in fact, when you take the number of particles going to infinity, you can show the distribution of your sample x star, okay, of your algorithm converge weakly to pi. But here, okay, the caveat of this method is okay, that to be effective in general, you need to take the number of particles which is exponential in the dimension. And so to circumvent this issue, it has been suggested to design a Markov chain for which pi will be invariance, and in the following this scheme, which is here. So here I want to define a Markov chain yn. So given the current state of my chain yn, here I will still use in fact some particle, n particle. I initialized in fact my first particle iteration n plus 1 as yn, so my current state of my Markov chain. I sample the n minus 1 other particle according to my reference measure. Then, okay, as here, I sample my index as a multinomial with appropriate weights, L tilde of xi n plus 1, and set that my next state of my Markov chain is equals to x n plus 1 e n plus 1. So here you can show that in fact yn is indeed a Markov chain for which pi is invariant, and in fact it is a partially what is called a partially collapsed Gibbs sampler, okay, meaning that you can show that if you extend the process yn and add the index process in and all the particles, in fact this algorithm has for invariant distribution this extended targets, okay, and if you marginalize this target with respect to y, you end up with your will targets pi. Okay. So now comes the ugly part. So now, okay, I want to adapt CIR and ECIR using Neo. So here what I will in fact consider, in fact I will extend the CIR and ECIR using this time not only the weights associated with L tilde or L associated previously, but I will use in fact all the weights of Neo. Okay, so here the algorithm works like this to define the counterpart of CIR for Neo. So here you draw n particles according to rho. You compute, of course, all the orbits associated with all the particles. You compute all the estimator of the normalizing constant associated with each particle, Z var p xi here. So it is just one, the Neo estimator associated with each particle. Now you need, okay, so now what you have, maybe I can take a picture. So here I have x1, x2, x3. Now, okay, based on this particle, I have some orbits. So T x1, T x2, T x3, and so it's I mess with the index x1, and the same here. So here, what you want to first select, you want first to select which particle you want to select. So here, which of x1 you want to select, and for this, okay, you consider you select the index of the particle according to a multinomial proportional to the normalizing to the Neo estimator of the normalizing constant associated with each particle. And then, okay, once you have selected, in fact, the particle based on this weight, you need to choose which iterate of your orbit you want to select. And here, the iteration index k, okay, meaning the number of iterations in your orbits, are selecting according to this weight. Okay. And now, okay, the final output u is equals to xkr. Okay. So here we end up with a new estimator, okay, which is as here unfortunately biased. Okay. But still, okay, we can adapt this estimator to incorporate this in a partially collapsed Gibbs algorithm, as is here, and end up with this MCMC scheme. So here, okay, I want to still define a Markov chain Yn as follows. So first, okay, as here, I initialize my particle xin+1 as my current state. I sample all the other particles according to rho. I first select the index of the orbit I will choose, with probability proportional to the Neo estimator for each particle, and then set Yn+1 at xn+1 In+1. So here Yn+1 consists of the selected particle, but still, in fact, now you need to add another step, where you need to choose the sample in the orbit, and for this you need to sample some iteration kn+1 according to this weight, and output un+1 as the kn iterates of t applied to yn+1. So here, in fact, compared to here, what is important is that you don't only have yn. Yn, in fact, corresponds to the particle you have selected, but the real sample which will target pi will be, in fact, the un+1. But once, in fact, you have yn, and in fact, once you have yn, in fact, you can directly, in fact, sample un+1 independently. So here, so we can have some theory about it. So you can write the Markov chain. We can have a large number and an ergodic theorem. So I have out of time, but I am happy to discuss about these results. We can have also uniform ergodicity with very strong assumption, but still, as usual. And here, I just want to give you some numerical results. So here, I consider the Gaussian model I presented you before in dimension 40, and I compare the Neo MCMC algorithm, which I presented you just before, with coordinated this here and the new U-turn. And so here on the right, you can see that our method are able to recover all the mode in comparison to correlated is here and the no U-turn. And to finish with, I will talk about some in-paging problem where so here we have selected a train VIE on several data sets, and now we divide images in two parts. So here we hide the bottom of the images and keep the top. And here, what we want to reconstruct, we want to reconstruct based on the train VIE. We want to reconstruct the bottom of the image. And for this, we consider a two-stage Gibbs sampler procedure, where what we want to sample efficiently from theta star YB given YT, and for this, we sample first p theta star z, so z is a hidden variable given your current estimation of the image, and then you update your belief, and so you sample p theta star YB given your new sample z and YT. So here, stage 2 is quite simple, because you have the train VIE, so it just consists in using your VIE, the train VIE. And now the challenging part is, as I present you in the introduction, sampling from the posterior of z given the current estimation of the image. And so here we consider for this ECIR and HMC for this task. And here are the results. So don't look at the last line here. It's just confuse you. It will just confuse you. But here, at the first, here you have ECIR, HMC, and Neo MCMC. So you can see that we are able to reconstruct more efficiently images compared to our competitor algorithm. So I will conclude here and thank you very much.
Thank you. We have time for one quick question. Yes, Marylou. Oh.
So maybe it's obvious, but how is it complicated to compute the weight WK of X? Is it straightforward, or does it require the...
In fact, in the case where you, if you use Conformal, in fact, it is very relatively easy. In the case you don't use, in fact, it all depends on the Jacobian, in fact, of your transformation. If the Jacobian is easy to compute, the weight are quite straightforward. Otherwise, no, it's a pain, of course.
Can I ask a really quick follow-up?
Yeah.
There were some additional weights that you could choose, right?
Yes,
And
exactly.
how do you choose those?
So, for the moment, we just choose the uniform one. But still, okay, we have in plan, in fact, to try to adapt them, of course.
Thank you again, Alain, for this nice talk. So what's the program now? So we have a coffee break until 11:15. And 11:15 sharp, we reconvene at the entrance of the building, and we will move to the room where Freddy will give the colloquium talk of this conference. Okay? So coffee and at 11:15 at the entrance of the building. Thank you.